Deep beyond the realm of ordinary stars lies a theoretical frontier, a star so dense that its neutrons give way to their own building blocks, quarks. In this frontier resides the quark star, a compact remnant that may sit just short of collapsing into a black hole. Today we journey into what these strange objects could be, how they form, and why they challenge our understanding of matter under extreme gravity. If you thrive on cosmic extremes and the cutting edge of astrophysics, please like, subscribe and share, and tell us in the comments what question would you ask about an object denser than a neutron star yet not quite a black hole. Thank you for watching. Now let's begin. A massive star begins as a quiet density ripple inside a cold cloud of gas and dust in a galaxy. Gravity slowly gathers more material into this slightly heavier patch, and over many hundreds of thousands of years the cloud core contracts, warms and spins. As the core shrinks, random motions of atoms and molecules turn into ordered inward flow, and the central region becomes denser and hotter than the surroundings. Radiation from the forming star is still weak at this stage, so the outer cloud remains dark in visible light, and only long wavelength observations reveal the hidden growth of a new massive star. As the core reaches higher temperatures of many thousands of degrees, hydrogen atoms collide more often and move at higher speeds, and the inner pressure rises enough to slow the collapse. In the very center, the density becomes so high that the material transitions smoothly into a hot ionized plasma, a state where electrons no longer remain bound to single atoms. Turbulent structures, filaments and clumps inside the cloud continue to feed material onto the growing protostar, and the mass of the central object increases rapidly, compared with lower mass stars. Because a massive star needs to accumulate many times the mass of the Sun, it must draw in gas from a large volume of the cloud, and this process shapes the surrounding environment. Jets and outflows driven by magnetic fields and rotation carry material away along the star's poles, while radiation pressure slowly begins to clear cavities in the surrounding gas. Over time, the forming star becomes visible in infrared, and then in shorter wavelengths as its surface temperature climbs and it settles onto what astronomers call the main sequence, the long central phase of a star's life, in which hydrogen fusion in the core supports the star against gravity. For a massive star, this main sequence phase is intense, but relatively brief. Its high core temperature and pressure drive nuclear reactions at a much faster rate than in a star like the Sun, so it burns through its hydrogen fuel in only a few million to a few tens of millions of years. During this stage, the star shines with a luminosity that can be tens of thousands to hundreds of thousands of times greater than that of the Sun, bathing its surroundings in energetic photons. These photons ionize nearby gas, forming bright emission regions, and their pressure can disrupt leftover parts of the original cloud, halting further star formation in the immediate neighborhood, while triggering new collapse in more distant regions. Inside the star, the balance between gravity pulling inward and thermal, and radiation pressure pushing outward remains steady, and the star maintains a stable radius. Convection and radiation transport energy from the core to the surface, and in the outer layers, strong stellar winds peel away mass over time. The rate of mass loss depends on the star's initial mass composition and rotation, but for the most massive stars, the winds can remove several solar masses of material during the main sequence alone. As hydrogen in the core becomes depleted, the internal structure of the star changes. The core gradually fills with helium, the ash of hydrogen fusion, and once the hydrogen fraction in the center falls below a critical level, the core can no longer produce enough energy to counter gravity through the same set of reactions. The core contracts and heats up further, while hydrogen fusion continues in a shell around the core. This change in the energy source leads the star to expand and cool at its surface, moving it away from its original position on the main sequence. Depending on its mass, the star may become a blue supergiant, a yellow supergiant, or a red supergiant, with its outer layers swelling to many hundreds or even more than 1,000 times the radius of the Sun. Despite this swelling, most of the mass remains concentrated in the core and inner regions where new fusion reactions now begin. At the higher temperatures reached in the contracted core, helium nuclei can fuse into heavier elements such as carbon and oxygen. This helium burning phase is shorter than the hydrogen burning phase, and for the most massive stars it may last only a few 100,000 years. As helium becomes exhausted in the core, the process repeats. The core contracts, again heats up, and new stages of fusion switch on, producing progressively heavier nuclei, such as neon magnesium, silicon, and eventually iron group elements. Each stage of fusion occurs on a shorter timescale than the previous one, so the late life of a massive star is marked by a sequence of increasingly rapid structural changes. In the outer layers, the star may show signs of instability with variable brightness and strong mass loss episodes. Dense stellar winds and eruptions enrich the surrounding interstellar medium with elements created in the star's interior, forming circumstellar shells and nebulae that record the star's mass loss history. Rotation and magnetic fields can complicate this picture, mixing material between different layers and altering how quickly fresh fuel reaches the core. In some massive stars, rotation-driven mixing can prolong certain fusion stages by feeding additional hydrogen or helium into the core, while in others, strong mass loss can strip away the outer hydrogen envelope, entirely revealing deeper layers at the surface. Throughout this complex evolution, the central theme remains. The same gravity steadily drives the core toward higher densities and temperatures, while nuclear fusion acts as a temporary support generating energy that holds up the star against its own weight. The more massive the star, the more extreme this competition becomes, and the more rapidly nuclear reactions must proceed to balance gravity. Eventually, the innermost regions approach conditions under which fusion can no longer produce energy efficiently from heavier and heavier nuclei. At that point, although the outer layers may still respond over longer timescales, the core stands on the brink of a rapid internal change that will mark the end of the star's life as an ordinary luminous object and prepare the stage for the compact remnant that follows. The core of a massive star approaches the end of its life in a quiet but decisive way. Deep inside, fusion has built up an onion-like structure of shells, each one burning a different nuclear fuel, while the very center holds a dense mixture dominated by the heaviest elements that the star can form in equilibrium. In the final stages, silicon burning in the innermost shell produces iron group nuclei in a relatively short time, and these nuclei cannot release energy by further fusion under the conditions in the star. For a while, thermal pressure and the pressure from degenerate electrons in the core still balance gravity, and the star continues to shine, although subtle changes in brightness and mass loss may already reflect the tensions building inside. As iron group material accumulates and the core mass grows beyond a critical fraction of the star's mass, the pressure support becomes fragile. The density climbs to values far beyond those in ordinary matter, and the separation between atomic nuclei shrinks until they are closely packed. At these densities and temperatures, several processes undermine the remaining support. High-energy photons begin to break apart some of the iron group nuclei, a process called photodisintegration, which absorbs energy rather than releasing it. At the same time, electrons are captured by protons inside nuclei, turning them into neutrons and emitting neutrinos, This electron capture removes part of the pressure from the degenerate electron gas, further weakening the resistance to gravity. Once the core exceeds its effective support limit, collapse accelerates. The inner core starts to fall inward, almost freely contracting from a size comparable to that of a small world toward something much smaller in a very short time. The infall speeds reach a significant fraction of the speed of light, and in the final instance the density crosses nuclear density, the regime in which nucleons are packed together as tightly as they are inside individual nuclei. At this point, repulsive components of the strong nuclear force and the effects of neutron degeneracy pressure abruptly stiffen the core. The inner region halts its collapse and rebounds slightly, sending a pressure wave outward into the still infalling outer core. This rebound alone is not enough to drive off the star's envelope, but it sets the stage for the emergence of a powerful shock wave. As the shock moves outward, it loses energy by breaking apart heavy nuclei and by emitting neutrinos, and in early models it tends to stall. Modern simulations suggest that the flood of neutrinos streaming out from the newly formed compact object can deposit enough energy in the layers just behind the stalled shock to revive it. Under the right conditions, the shock regains strength, plows through the remaining overlying material, and disrupts the star in a core collapse supernova. To an external observer, this event appears as a sudden brightening that can outshine an entire galaxy for days to weeks, followed by a slower decline, as radioactive decay in the ejected material powers the fading light. The debris from the explosion carries heavy elements into the surrounding interstellar medium, enriching future generations of stars and planets. While the outer layers race outward, the fate of the central remnant is sealed by the mass left behind in the collapsed core and the behavior of matter at extreme density. If the final core mass falls within a certain range neutron degeneracy pressure, and nuclear forces can halt the collapse at a radius of only a few tens of kilometers, forming a neutron star. In this case, the remnant emerges as a rapidly rotating, highly magnetized object that will later reveal itself through pulses or other radiation, but at the moment of birth, it is simply an extremely hot compact core cooling by neutrino emission. If the core is more massive, gravity may overwhelm all possible pressure support, and the collapse may continue past the neutron star stage. The matter then crosses its own event horizon, and a stellar mass black hole forms, hidden from direct view but detectable through its influence on nearby matter and light. The precise dividing line between these outcomes depends on the equation of state of dense matter, the details of the explosion, and the mass of material that falls back onto the remnant after the initial blast. There may be cases in which a core that would otherwise form a neutron star accretes additional matter from the infalling envelope and is pushed over the threshold into black hole formation. There may also be cases in which rapid rotation or magnetic fields change how mass and angular momentum are redistributed during collapse, altering the outcome. Across these possibilities, the end of a massive star's life marks a transition from a large luminous object spanning many millions of kilometers to a compact remnant measured in only a few tens of kilometers, or in the case of a black hole, to a region from which no light can escape. As the newborn compact remnant settles, it emits an intense burst of neutrinos over a period of only a few tens of seconds, carrying away much of the gravitational binding energy released in the collapse. These neutrinos interact only weakly with ordinary matter, so most of them escape directly into space, but a small fraction deposit energy in the surrounding material and help shape the dynamics of the explosion. In the minutes and hours that follow, shock-heated gas expands and cools, and the star's former outer layers begin their long journey into the galaxy as a supernova remnant. Over thousands to tens of thousands of years, this expanding shell sweeps up interstellar gas forms, complex filaments, and gradually merges back into the diffuse medium. Long after the brief flash of the supernova has faded from view, the compact remnant remains as a persistent trace of the core collapse, quietly evolving in isolation or within a binary system. A neutron star stands as the smallest and densest confirmed kind of stellar remnant before the threshold of a black hole, and it does so in a quiet, compact way that hides its extremes behind a simple appearance. After a core collapse, supernova leaves behind a suitable core gravity, compresses the matter into an object with a mass comparable to that of the Sun, or a few times that value, yet packed into a sphere only a few tens of kilometers across. The result is a body whose average density lies far beyond anything found in ordinary planets, white dwarfs, or even the central regions of normal stars. In this environment, atoms no longer exist as familiar structures with nuclei surrounded by electron clouds. Under the intense pressure, electrons and protons inside the former stellar core have largely combined to form neutrons and matter approaches, a state sometimes called neutron-rich nuclear matter, where nucleons sit almost shoulder to shoulder with very little empty space between them. The gravity at the surface of such an object is so strong that it demands a description in terms of general relativity rather than everyday Newtonian gravity. The space-time in the immediate surroundings is strongly curved, and this curvature affects the path of light trying to escape. Photons climbing away from the surface lose energy, shifting to longer wavelengths in a process known as gravitational redshift, so the spectrum of radiation seen by a distant observer carries an imprint of the neutron star's extreme gravity. If a small object were somehow placed just above the surface, it would feel an acceleration many billions of times stronger than that on Earth, and no known material could withstand such forces without being torn apart. Despite this, the neutron star itself remains stable, because the inward pull of gravity is balanced by the combined effect of neutron degeneracy pressure and the repulsive part of the strong nuclear force at very short distances. Degeneracy pressure arises from the quantum mechanical principle that identical fermions such as neutrons cannot all occupy the same quantum state. As gravity tries to squeeze the neutrons closer together, this principle resists further compression, creating a pressure that does not depend on temperature in the same way as ordinary gas pressure. At densities near and above nuclear density, the short-range repulsion between nucleons also becomes important, further stiffening the response of matter to compression. Together, these effects allow the star to settle into a stable configuration over a wide range of masses below a certain maximum. The surface of a neutron star is not a place with gentle conditions. The escape speed, the speed needed for a particle to leave the star and never return, is a large fraction of the speed of light. The outermost layer may be only a few centimeters to a few meters thick, if defined by a sudden change in composition. Yet in that shallow region, the pressure can rise from values comparable to those inside ordinary stars to values associated with dense nuclear matter. The crust beneath this surface is incredibly rigid compared with normal solid materials, and can support strong stresses before yielding, although its resistance is still limited. As a result, slight shifts or fractures in this solid outer layer can alter the star's rotation or magnetic field configuration in measurable ways, though the detailed structure of the crust belongs to the interior picture that unfolds later. Thermal conditions in a freshly formed neutron star are also extreme. Right after birth, the interior temperature far exceeds that of ordinary stellar cores, and the star cools primarily by emitting neutrinos from its dense interior. Over time, the neutrino emission weakens and surface photon emission becomes more important. To a distant observer, the star appears as a faint, small, hot object, radiating mainly in X-rays with a surface temperature that decreases gradually over hundreds of thousands to millions of years. Measuring that cooling curve helps astrophysicists infer properties of the dense matter inside, turning each neutron star into a natural laboratory for physics at densities that cannot be reproduced on Earth. The compact size and high density also influence how the star responds to rotation. Conservation of angular momentum during collapse means that a remnant formed from a massive star core often spins rapidly. Even a modest initial spin in the progenitor core can translate into rotation periods of only fractions of a second once the core contracts to neutron star size. The small moment of inertia combined with strong gravity and high density produces a system in which even tiny changes in internal structure or angular momentum distribution can lead to observable changes in the spin rate. Some neutron stars show sudden small increases in rotation speed events, known as glitches, which are interpreted as signs of internal rearrangements, or the interaction between a superfluid component inside and the solid crust. The high density of charge carriers in the interior and the original magnetic field of the progenitor star combine during collapse to produce magnetic fields that can be many orders of magnitude stronger than those found on ordinary stars. For many neutron stars, these intense magnetic fields guide charged particles and shape the emission of radiation, although the detailed behavior of magnetism belongs mainly to the next step of the story. At this stage, it is enough to note that the interplay of gravity, density, and magnetism makes each neutron star a compact system where multiple branches of physics meet. Observationally, neutron stars reveal themselves in several ways. Some are isolated objects visible only through their thermal emission in X-rays as they cool slowly over time. Others reside in binary systems where they accrete matter from a companion star. In such systems, gas spirals inward in an accretion disk, heats up to high temperatures, and emits X-rays before falling onto the neutron star surface, providing a way to probe both the gravity field and the behavior of matter in strong fields. Still others spin rapidly and emit beams of radiation that sweep through space. These are recognized as pulsars when the beams cross our line of sight and produce regular flashes. Across all of these manifestations, the underlying object remains the same, a compact remnant with mass, comparable to that of a normal star compressed into a radius only a little larger than that of a city where matter reaches densities at or above those in atomic nuclei, and where the familiar separation between particle physics, nuclear physics, and astrophysics becomes blurred. Within the current framework of observations, neutron stars occupy the status of the densest confirmed stellar objects that still have a physical surface from which light can escape. More massive remnants appear to collapse further and form black holes where gravity becomes strong enough to create an event horizon. Less dense remnants, such as white dwarfs, remain far from nuclear density and show different behavior. The place of neutron stars between these two regimes gives them special importance, because studying them helps to define the boundary between matter, supported by known forms of pressure, and matter that has succumbed to complete gravitational collapse. By measuring their masses, radii, and temperatures, and by tracking their cooling and rotation over time, astronomers gradually refine the range of possible equations of state that describe dense matter and improve the understanding of how nature behaves at densities that cannot be reached in terrestrial laboratories. In this way, each neutron star stands quietly as an extreme but stable outcome of stellar evolution, marking the point at which confirmed physics of compact objects reaches its current limit before the domain where collapse leads to a black hole. A neutron star rarely sits still. When the core of a massive star collapses, the angular momentum of the original core is largely conserved, so the much smaller remnant typically spins rapidly. A slowly rotating stellar core that turns only a few times in many days can, after collapse to neutron star size, become an object that completes a rotation in fractions of a second. The precise spin period depends on how fast the progenitor core rotates, how mass and angular momentum are redistributed during collapse, and how much material falls back after the explosion, but the general outcome is a compact object whose rotation is far quicker than that of ordinary stars or planets. This rapid spin is one of the most striking macroscopic properties of neutron stars, and it plays a central role in how these objects interact with their surroundings and how they are seen from far away. As the star collapses, not only angular momentum but also magnetic flux is approximately conserved. The progenitor star's magnetic field, already present but modest in strength, becomes compressed and strengthened as the stellar material shrinks inward. The result is a magnetic field at the surface of the neutron star that can be many orders of magnitude stronger than that of the parent star. Even a relatively ordinary neutron star can carry a field trillions of times stronger than the magnetic field at the surface of Earth, while a subgroup called magnetars hosts fields that are stronger still. These magnetic fields thread the surrounding space and anchor themselves in the crust and interior of the star, defining a preferred axis that need not align with the axis of rotation. The combination of rapid spin and strong magnetic field gives rise to a magnetosphere, a region around the star filled with plasma, whose motion is governed by the magnetic field lines and the rotation of the star. Charged particles in this region are constrained to move along magnetic field lines and are accelerated by electric fields induced by the rotating magnetic field. These particles emit radiation across a wide range of wavelengths, including radio waves, X-rays, and sometimes gamma rays. When the magnetic axis is tilted relative to the rotation axis, the regions of strongest emission form beams that sweep through space as the star spins. If one of these beams crosses the line of sight of an observer, the observer records a sequence of pulses, each corresponding to one rotation of the neutron star. Objects that reveal themselves this way are called pulsars. To a detector, the pulses appear as regular flashes repeating with a period equal to the star's rotation period. Some pulsars rotate once every few seconds, while others, called millisecond pulsars, complete hundreds of rotations in a single second. The extraordinary regularity of these pulses makes pulsars natural cosmic clocks. Over timescales of years, the arrival times of pulses can be predicted with great precision, and any deviations from this regularity can reveal subtle physical processes. The pulses also reflect the geometry of the magnetic field and the distribution of emitting regions above the star, so they provide indirect information about the structure of the magnetosphere. In isolated pulsars, the rotation gradually slows as the star loses rotational energy. This spin down is thought to be driven primarily by the emission of electromagnetic radiation and the outflow of charged particles along open magnetic field lines. As the star loses energy, its period lengthens and the pulse spacing changes in a predictable way. By measuring both the current period and the rate of change of the period, astronomers can estimate a characteristic age for the pulsar and infer the strength of its magnetic field under simple models. In many cases, the inferred ages are compatible with the ages of surrounding supernova remnants, reinforcing the link between core collapse and pulsar birth. The spin down is not always perfectly smooth. Many pulsars exhibit small, sudden changes in their rotation rate called glitches. In a glitch, the star's period decreases slightly, meaning the star spins a little faster than before. Afterward, the period often relaxes slowly toward the previous trend. These events are interpreted as signs of internal rearrangements, such as adjustments in the solid crust or interactions between a superfluid component in the interior and the rest of the star. Although the detailed microphysics belongs to later discussion at this stage, glitches can be seen as macroscopic markers of the complex internal structure that lies beneath the surface. Some neutron stars, especially those in binary systems, experience a different kind of rotational evolution. When a neutron star orbits a companion star and accretes matter from it, the inflowing gas can transfer angular momentum to the compact object. Over long periods, this process can spin the neutron star up to very short periods, creating millisecond pulsars. These old rapidly rotating neutron stars have comparatively weaker magnetic fields at the surface, either because their fields have decayed or because accretion has altered the field configuration. Millisecond pulsars also emit pulses with remarkable stability and serve as especially precise clocks. Arrays of these pulsars observed over many years are used to search for very low-frequency gravitational waves passing through the region of space containing the solar system, because such waves would cause tiny correlated shifts in the arrival times of pulses from different directions. The electromagnetic output of a neutron star also depends on its magnetic field geometry and strength. In some objects, the magnetic field is so intense that it dominates the behavior of the crust in the magnetosphere. These magnetars can produce bursts of high-energy radiation when their magnetic fields rearrange or when the crust yields under the stress of the field. Short, intense flashes of X-rays and gamma rays from magnetars demonstrate that magnetic energy stored in the field can be converted into radiation on short timescales. In quieter periods, magnetars emit persistent X-rays powered by the decay of their magnetic fields, rather than by residual heat alone. Across the broader population of neutron stars, magnetic fields vary in strength and configuration, but they generally remain strong enough to shape the star's interaction with its environment. In binary systems, accretion onto a magnetized neutron star can be channeled along field lines toward the magnetic poles, forming hotspots where infalling gas hits the surface. As the star rotates, these hotspots produce X-ray pulsations, allowing observers to measure the spin and to infer details about the field geometry and the accretion flow. In systems with stronger magnetic fields and lower accretion rates, the magnetosphere can even prevent matter from reaching the surface, instead ejecting it back into space in a process that further alters the spin rate. Observational techniques that combine radio X-ray and gamma-ray data build a more complete picture of neutron star magnetism and rotation. Radio telescopes track the timing and shape of pulses. X-ray observatories record the thermal emission from the surface, and from accretion, hotspots and gamma-ray instruments capture the highest energy photons from outer magnetospheric regions. Together, these data sets show that spin and magnetic field are closely linked parameters that govern much of a neutron star's behavior. In some systems, precise timing of pulses in binary orbits provides test of general relativity, as the strong gravitational fields and rapid orbital motion produce measurable relativistic effects on the pulse arrival times. In all of these cases, the underlying compact object remains the same, a dense remnant whose spin and magnetic field, inherited and amplified during core collapse, define how it radiates and evolves. By following these properties over time, astronomers trace the life of neutron stars from newly born rapidly spinning pulsars surrounded by supernova debris, through middle-aged objects with slower spins and cooler surfaces, to old recycled millisecond pulsars in long-lived binaries. Throughout this progression, rotation and magnetism act as the visible and measurable signatures of the otherwise hidden interior, turning each neutron star into a beacon that carries information about extreme gravity and dense matter out into the surrounding space. The interior of a neutron star can be imagined as a set of layers arranged by depth and density, although in reality the transitions between these regions are gradual rather than sharply stepped. Starting just beneath the surface, there is a thin atmosphere of ionized particles, only a few centimeters to a few meters thick depending on how it is defined. This atmosphere is held tightly by gravity and shaped by the star's magnetic field, so its structure is very different from the extended gaseous envelopes of ordinary stars. Below this thin layer lies the outer crust, a region in which atomic nuclei are arranged in a dense lattice, surrounded by a sea of highly degenerate electrons. Degeneracy here means that the electrons fill all the available low-energy quantum states, so the pressure they exert arises largely from quantum mechanical principles rather than from thermal motion. The nuclei in the outer crust carry large positive charges and sit in fixed positions, forming something like a crystal of extremely neutron-rich nuclei. As depth increases, the pressure grows and electrons are forced into higher energy states, gradually pushing nuclear matter to become more neutron-rich through processes such as electron capture. The composition of these nuclei is determined by a balance between nuclear-binding electron degeneracy and the surrounding pressure. Moving deeper, one reaches the inner crust, where densities become high enough that some neutrons are no longer bound inside nuclei and begin to drip out into the surrounding medium. In this region, the matter consists of a mixture of neutron-rich nuclei, free neutrons, and degenerate electrons. The nuclei themselves may adopt complex shapes as they try to minimize their energy under the competing influences of nuclear attraction and Coulomb repulsion. Theoretical studies suggest that these shapes can include rods, slabs, and more intricate forms which together are sometimes referred to as nuclear pasta. The free neutrons in the inner crust are expected to behave as a quantum fluid, and under many models form a superfluid, a state in which they flow without viscosity. The presence of this superfluid component, together with the rigid lattice of nuclei, makes the inner crust a mechanically and dynamically rich region that can support elastic stresses and allow relative motion between different components. These properties are thought to be important for phenomena such as glitches in pulsar rotation, though the detailed microphysics remains an area of active research. Deeper still, at densities near and above that found inside atomic nuclei, the separation between individual nuclei disappears. The nuclei dissolve into a continuous fluid of nucleons, and one enters the outer core of the star. In this region, matter is composed primarily of neutrons with a smaller fraction of protons, electrons, and often muons, which are heavier relatives of electrons that appear when the energy of the system is high enough to make their presence favorable. The neutrons may form a superfluid, while the protons can form a superconducting condensate, meaning they move collectively in a way that expels magnetic fields from certain regions or channels them into concentrated flux tubes. These quantum states influence how heat and momentum are transported inside the star and how the star's magnetic field evolves over time. The pressure support in the outer core arises from nucleon degeneracy nuclear interactions, and the contributions of the leptons and the relationship between this pressure and the density is described by what physicists call the equation of state. This equation of state is central to the star's structure. For a given central density, it determines how pressure changes with radius, and thus fixes the mass and radius for a stable configuration. A stiffer equation of state in which pressure rises quickly with density allows the star to support more mass for a given radius, while a softer equation of state leads to smaller maximum masses and more compact stars. Observational measurements of neutron star masses and radii therefore provide crucial constraints on the possible forms of the equation of state. When astronomers find neutron stars with masses around or above about 2 solar masses, those measurements tend to rule out very soft equations of state that would not support such heavy stars. As one moves further inward, the density in the inner core may reach several times nuclear density. In this regime, the composition and behavior of matter are much less certain. Some models suggest that additional particle species such as hyperons, which contain strange quarks, may appear at these densities. Other models allow for condensates of mesons, which are particles composed of a quark and an antiquark, to form. Each of these possibilities changes the balance of pressure and energy, and thus affects the equation of state. However, the presence and abundance of such components cannot yet be confirmed directly, and different theoretical approaches yield different predictions. In many calculations, the inner core remains dominated by strongly interacting nucleons, with the detailed form of their interactions adjusted to match known properties of nuclear matter and extrapolated into the high-density regime. Regardless of the exact composition, the inner core is the region where the densities become high enough that more exotic phases of matter may appear, and where the question of whether nucleons remain intact or begin to merge into new states such as deconfined quark matter becomes most pressing. At this stage in the description, however, matter is still treated primarily as interacting nucleons and leptons, without assuming a full transformation into quark matter. The balance between gravity and internal pressure in these layers produces characteristic density and pressure profiles. The outer crust, outer core, and inner core each occupy different radial extents, depending on the stellar mass and the chosen equation of state. More massive neutron stars tend to have smaller radii for the same equation of state, and develop larger regions at very high density in their cores, while less massive stars are less compact and maintain larger crusts. The thickness and composition of the crust influence how the star cools and how its magnetic field threads the interior, while the conditions in the core determine how much mass the star can support before further collapse becomes inevitable. From a thermal perspective, the interior is initially almost isothermal soon after formation, with heat transported efficiently by neutrinos and conduction. As the star ages, temperature gradients can develop, especially near the crust-core boundary. Cooling proceeds fastest through neutrino emission processes in the dense core, such as modified Urca reactions that involve nucleons and leptons, and possibly more rapid direct Urca processes if the composition allows. The presence or absence of superfluid and superconducting phases alters these cooling channels by suppressing some reaction rates and opening others, such as neutrino emission, associated with the formation of Cooper pairs of nucleons. By comparing observed surface temperatures and ages of neutron stars with theoretical cooling curves, astrophysicists attempt to infer which processes are active in the interior, and hence which equations of state remain viable. Throughout this layered structure, general relativity governs the global balance between gravity and pressure. The metric inside the star, which describes how spacetime is curved by the mass and pressure of the matter, must be solved together with the equation of state to yield consistent models of mass radius and internal profiles. The resulting solutions reveal that pressure itself contributes to the gravitational field, so it is not only the mass density, but also the internal energy and stresses that curve spacetime. In practice, this means that small changes in the equation of state at high densities can have significant effects on the maximum mass and compactness of neutron stars. In summary, the inside of a neutron star can be viewed as a continuous progression from a solid lattice of nuclei and electrons near the surface through mixed faces of nuclei and superfluid neutrons in the crust, into a dense fluid of nucleons and leptons in the core, where the equation of state is controlled by strong nuclear forces and quantum degeneracy. At the greatest depths, the densities and pressures reach ranges where current nuclear physics and astrophysical models begin to diverge, setting the stage for the next step in the exploration, which considers how and where this nuclear matter might give way to even more compressed states. At the greatest depths inside a neutron star, the density and pressure approach levels where the familiar description of matter as a collection of neutrons, protons and leptons may no longer be sufficient. In the outer core and much of the inner core, nucleons remain the main carriers of mass and pressure, interacting through the strong nuclear force in ways that can be modelled, at least approximately, by extending laboratory measurements of nuclear matter. As the density rises to several times the value found inside atomic nuclei, however, the average spacing between nucleons shrinks so far that their internal structure made of quarks bound together by gluons becomes increasingly relevant. Quantum chromodynamics. The theory that describes how quarks and gluons interact predicts that under conditions of extremely high density or temperature, quarks may become deconfined, meaning they are no longer locked into individual nucleons, but move in a collective state often called quark matter. Inside a compact star, this deconfinement, if it occurs, would not happen everywhere at once. Instead, there is likely to be a gradual transition region, where matter changes from a description in terms of nucleons to one in terms of quarks. The nature of this transition is uncertain. Some theoretical models treat it as a sharp first-order phase change in which pressure and density follow one relation on the nuclear side and a different relation on the quark side with a distinct boundary between them. Other models suggest a smoother crossover where nucleon-like and quark-like degrees of freedom coexist over a range of densities. The details depend on how the strong interaction behaves in a regime that is difficult to explore, either in experiments or in straightforward calculations, so a family of possible equations of state exists, rather than a single agreed description. From the point of view of stellar structure, the key effect of a transition toward quark matter is a change in how pressure responds to further compression. If the appearance of quark degrees of freedom softens the equation of state, meaning the pressure rises more slowly with density, then the star becomes more compressible. For a fixed mass, the radius decreases, and the central density becomes higher than in a purely nucleonic model. If, on the other hand, strong repulsive interactions among quarks or pairing effects stiffen the equation of state at high density, the star can support larger masses without collapsing and may not shrink as much. Astrophysical observations, especially measurements of neutron star masses and radii, are beginning to limit which of these possibilities remain viable, but they do not yet single out a unique answer. In many scenarios, the transition to quark matter, if it occurs, is expected first in the very center of the most massive neutron stars. Less massive stars never reach the required central density, so they remain entirely within the nuclear matter regime. More massive stars with higher central pressures can cross the threshold where nucleons begin to overlap strongly and deconfinement becomes energetically favorable. In such stars, the innermost region may contain a core where quark matter dominates, surrounded by layers where nucleonic matter still provides most of the pressure support. The radius of this inner region depends on the star's mass and on the chosen equation of state, and it can range from a negligible fraction of the total radius to a significant portion of the interior. A useful way to think about this boundary is to consider how the composition changes with depth. At lower densities, matter consists mainly of heavy nuclei in a lattice, then of neutrons, and a smaller fraction of protons and leptons in a fluid state. As depth increases, the proportion of neutrons rises, and additional particle species may appear. Beyond some critical density model dependent but typically A few times nuclear density quark degrees of freedom may gradually emerge. In some parameter, choices down and up quarks appear first, while strange quarks, which are heavier, enter only at still higher densities. In other choices, strange quarks are present from the start in a mixed phase. The emergence of quark matter changes the energy balance and the mechanical properties of the core, but all of these pictures remain rooted in theory rather than confirmed observation. Direct experimental access to such densities is not available in present-day laboratories. High-energy heavy ion collisions briefly create very hot dilute quark-gluon matter, but the conditions in those experiments differ from the cold dense regime inside a compact star. Numerical techniques that solve quantum chromodynamics on a spacetime lattice work well at high temperature and low net density, but face severe challenges at the high densities relevant for neutron star cores. As a result, astrophysicists rely on models that incorporate known aspects of the strong interaction, observational constraints from neutron star masses and radii, and basic thermodynamic principles to construct plausible equations of state that include a transition to quark matter. These models predict ranges of central density and pressure at which quark matter might appear, but the ranges are broad and different approaches can place the transition at quite different points. The uncertainty in the transition density means that the internal structure of the densest neutron stars is not uniquely defined. For one set of equations of state, a star with a given mass might host a substantial region of deconfined quark matter at its center. For another set, the same mass remains entirely in the nucleonic regime but lies close to the threshold. For still other models, pressures and densities never favor deconfinement before the star reaches the maximum mass that can be supported. In those cases, any attempt to compress the star further would lead directly to collapse into a black hole without passing through a phase where a stable quark core is present. Observations offer some indirect guidance. The existence of neutron stars with masses around 2 solar masses indicates that the equation of state cannot soften too much at moderate densities, because an overly soft equation of state would not support such heavy stars. This fact restricts how early in density any transition to softer quark-dominated matter can occur. At the same time, measurements of radii suggest that typical neutron stars are relatively compact, implying that the equation of state is not extremely stiff. Reconciling these constraints leaves room for transitions to quark matter at higher densities, but does not fix their details. In this context, the boundary between neutron-rich nuclear matter and possible quark matter inside a compact star is best understood as a region of parameter space where competing physical descriptions overlap and where current theory and observation still leave open multiple scenarios. The star's global properties, such as mass and radius, reflect an average over its internal composition, so different internal arrangements can sometimes produce similar external signatures. Nonetheless, the mere possibility that the central densities in the most massive neutron stars reach values high enough for deconfinement makes this boundary region a natural focus for studies of ultra-dense matter. It represents the point at which the standard nuclear picture may give way to a description in which quarks themselves, rather than the nucleons they form, become the relevant degrees of freedom for understanding how matter resists gravity in the heart of a compact star. In some theoretical descriptions, the path from ordinary neutron stars to fully deconfined quark stars passes through an intermediate class of objects often called hybrid stars, in which a core of quark matter sits inside an outer mantle of neutron-rich nuclear matter. In these models, the star begins its life after core collapse as an ordinary neutron star supported entirely by nucleonic matter and leptons as described earlier. As it cools, spins down, or accretes matter from a companion, its central density can rise gradually, pushing the inner core closer to the conditions where deconfinement of quarks becomes favorable. When the central pressure crosses a critical value, nucleons in the innermost region may rearrange into a new configuration where quarks are no longer confined into individual particles but move in a collective state. At that moment, the structure of the star adjusts to accommodate a small region of quark matter at the center, while the bulk of the star remains in the nuclear matter phase. The transition does not necessarily involve a violent macroscopic event. In many calculations, the change in composition and the associated change in the equation of state occur over a narrow range of density, so the star moves from one stable configuration to another as its internal conditions slowly evolve. The newly formed quark core has a radius much smaller than the overall size of the star, and its properties are set by the interplay between the pressure of quark matter and the weight of the overlying layers. Outside this core lies a region in which nuclear matter and quark matter may coexist in a mixed phase, depending on the chosen model. In such a mixed region, small domains of quark matter can be embedded in nuclear matter, or the reverse, forming structures that minimize the total energy under the combined influence of surface tension and long-range forces. Farther outward, the matter returns to the purely nucleonic composition already described for the outer core and crust, so an observer looking only at the surface would not see any immediate difference between a hybrid star and an ordinary neutron star of similar mass and radius. The presence of a quark core nonetheless alters the global relationship between mass and radius that the star can support. For a given total mass, a softer equation of state in the central region allows gravity to compress the core, more strongly increasing the central density. As a result, some hybrid configurations have slightly smaller radii than purely nucleonic stars of the same mass. In some models, the change in stiffness at the transition density produces a characteristic bend or extra branch in the curve that relates mass to radius, with one branch dominated by nuclear matter and another branch in which a quark core occupies a significant fraction of the interior. Under these conditions, two stable stellar configurations can exist with nearly the same mass, but different radii and internal composition, one without a quark core and one with a quark core. The exact details of this behavior depend sensitively on how the transition to quark matter is modeled, and on the parameters chosen for the strong interaction at high density. Hybrid stars also differ from ordinary neutron stars in their moments of inertia and tidal response. The distribution of mass inside the star determines how easily it deforms in a gravitational field and how it responds to external torques. A softer central equation of state associated with quark matter tends to concentrate more mass toward the center and can reduce the overall radius, thereby changing the moment of inertia. These differences show up in how a star's rotation evolves under electromagnetic braking, and in how two compact objects distort each other as they orbit closely in a binary system. Precision measurements of spin evolution and orbital dynamics, combined with gravitational wave observations, are therefore sensitive to the presence or absence of a soft central core. At the same time, the quark core influences how the star cools. The microscopic processes that produce neutrinos in quark matter differ from those in nucleonic matter and may proceed more quickly under some conditions. If quark matter allows particularly efficient neutrino emission, a hybrid star could cool faster than a purely nucleonic star of the same mass. If pairing of quarks into correlated states suppresses certain reactions or opens new channels, the cooling behavior could change in more complex ways. Observed surface temperatures of compact stars at different ages when compared to theoretical cooling curves, can thus favour or disfavour particular combinations of nuclear and quark matter in the interior, although uncertainties in the microphysics keep the conclusions tentative. Dynamic changes in the internal composition might also leave signatures in the star's rotational behaviour. As the central density rises over time in a spinning neutron star losing rotational energy, the core can move closer to the threshold for deconfinement. When the threshold is crossed, matter in the inner region transitions into quark matter, altering the internal density profile and pressure support. The star reacts by adjusting its radius and moment of inertia. Because angular momentum must be conserved, a decrease in the moment of inertia. At fixed angular momentum leads to a slight increase in the rotation rate, a process that could contribute to observed timing irregularities. Such interpretations rely on model-dependent assumptions and other mechanisms such as interactions between superfluid components, and the crust also provide explanations for glitches. The possible role of quark cores in these phenomena remains a topic of study rather than an established fact. From the perspective of global stability, hybrid stars lie between ordinary neutron stars and purely quark matter stars, on the sequence of solutions that arise from solving the gravitational equilibrium equations with different central densities. For low central densities, solutions resemble ordinary neutron stars with no quark matter. As central density increases, hybrid configurations appear once the threshold for the phase transition is reached. Beyond a certain maximum mass, no additional stable solutions exist, and further compression would lead to runaway collapse into a black hole. Whether the hybrid branch occupies a broad region in this sequence, or appears only in a narrow range of masses, depends on how strongly the equation of state softens and then stiffens across the transition. In some equations of state, the hybrid branch is short and may be difficult to populate in nature, while in others it extends over a significant mass range. The lack of direct observational markers makes it difficult at present to say which situation actually occurs inside real stars. In all of these scenarios, hybrid stars serve as a conceptual bridge between the well-established physics of neutron-rich nuclear matter and the less certain physics of deconfined quark matter. They provide a framework in which the onset of a new phase does not eliminate the familiar crust and outer layers of a neutron star, but adds a new central component whose properties are set by quantum chromodynamics at high density. By exploring how such stars would behave under different conditions, theorists can link microscopic assumptions about the strong interaction to macroscopic observables such as mass-radius rotation and cooling, and can outline how future measurements might distinguish between stars with purely nuclear interiors and those that host quark cores. At the present stage, hybrid stars remain hypothetical, but they encapsulate in a single object the boundary between two descriptions of matter, and they define the next inward step in the exploration of what lies inside the densest compact stars. In theoretical work on ultra-dense matter, a natural extension of hybrid configurations is the idea of a whole star composed largely or entirely of quark matter, an object often called a quark star. In this picture, the deconfinement of quarks does not remain confined to a small central core, but spreads until the entire interior and possibly almost all of the star is in a quark-dominated phase. The resulting object differs in important ways from a neutron star made of nucleons, even though it occupies a similar place in the overall sequence of stellar remnants between white dwarfs and black holes. A quark star is still a compact object held together primarily by its own gravity, but the internal pressure that resists further collapse arises from quark matter rather than from neutron-rich nuclear matter. The mass of such an object can be comparable to that of a neutron star in the range of about 1 to a few times the mass of the Sun, but the exact range of allowed masses depends on the assumed equation of state for quark matter. Because quark matter can respond differently to compression, the nuclear matter quark stars often appear in models as slightly smaller and denser than neutron stars of the same mass with radii of only a few kilometers to perhaps just over 10 kilometers, depending on the chosen parameters. In some scenarios, quark matter is treated as self-bound, meaning that even in the absence of gravity, it would remain a stable droplet due to the balance of internal interactions. In that case, the star's surface is defined not by the point where gravity fails to hold the outer layers, but by the point where the pressure and density of quark matter fall to the value characteristic of the stable state. Such a self-bound star can in principle have a smaller radius for a given mass than a purely gravitationally bound neutron star, because the internal pressure arises from the properties of the quark phase itself as well as from degeneracy and interaction forces. Other models treat quark matter as bound only by gravity, more like ordinary nuclear matter, in which case the star's structure is determined by the same balance between gravity and pressure as for neutron stars, but with a different relation between pressure and density. In both approaches, solving the equations of hydrostatic equilibrium, combined with the chosen quark matter equation of state, yields a family of possible quark star configurations, each one corresponding to a particular central density and mass. At low central densities, the solutions may resemble compact stars with small quark cores and extensive outer layers, while at higher central densities the quark phase can occupy nearly the entire interior. As the central density increases further, the sequence reaches a maximum mass beyond which no stable quark star configurations exist, and any additional compression would lead to collapse into a black hole. This maximum mass depends on how stiff or soft the quark matter equation of state is. Stiffer models can support more massive quark stars, while softer models lead to lower maximum masses and more compact objects. The outer structure of a quark star also depends on whether it carries any residual nuclear material at the surface. In some theoretical constructions, a quark star is bare with quark matter, extending all the way to a sharp boundary, where the pressure drops abruptly, and an electric field layer separates the quark phase from the vacuum. In others, a thin crust of ordinary nuclear matter sits on top of the quark core, supported by electrostatic forces, above a surface where the density changes sharply from nuclear values to those characteristic of quark matter. This crust, if present, would have a thickness of perhaps hundreds of meters to a kilometer or so, much thinner than the crust of a typical neutron star, and it would play a role in how the star interacts with accreted matter and in how its magnetic field attaches to the surface. From an external viewpoint, a quark star with a crust might look very similar to a neutron star, while a bare quark star could have a more unusual surface emission spectrum and electromagnetic environment. Global properties such as mass radius moment of inertia and tidal deformability are central to the macroscopic comparison between quark stars and neutron stars. The moment of inertia describes how the star's mass is distributed with radius, and thus influences how easily the star's rotation changes under torques. For a given mass, a more centrally condensed object with a smaller radius has a smaller moment of inertia than a less compact one. Tidal deformability measures how much the star's shape changes in response to the gravitational field of a companion. A softer internal equation of state, as often assumed for quark matter, usually leads to lower tidal deformability, meaning the star resists being deformed and remains more compact. Measurements of tidal effects and gravitational waves from merging compact binaries can therefore in principle distinguish between more and less compact configurations and between different classes of equations of state. In models where quark stars are self-bound, one distinctive feature is the possibility of low-mass compact stars with unusually small radii. Whereas neutron stars cannot be stable below a certain minimum mass because gravity is needed to compress nuclear matter to high density. A self-bound quark star could in theory exist at lower mass while remaining compact. Such low-mass quark stars would have weaker surface gravity, but still very high density compared with normal matter. Whether such objects can form in realistic astrophysical processes is uncertain, because core collapse supernova and other known channels tend to produce remnants with masses above a certain threshold. Nevertheless, the theoretical existence of stable configurations with different mass ranges is one of the macro-level distinctions between quark stars and neutron stars. Quark stars, if they exist, would also obey different sequences of stable configurations under changes in external conditions such as accretion or rotation. Adding mass to a quark star in a binary system would push it along its sequence of equilibrium solutions, increasing its central density and changing its radius. Rapid rotation can support additional mass against collapse by providing centrifugal support, so rotating quark stars may reach higher maximum masses than non-rotating ones, just as rotating neutron stars can. However, the specific relationship between mass spin and radius depends on the underlying equation of state, and therefore differs between quark-dominated and nucleon-dominated stars. In some cases, the presence of quark matter allows for more dramatic changes in structure when rotation slows, potentially affecting how the star's moment of inertia evolves as it spins down. Despite these differences, quark stars remain firmly hypothetical. No observed compact object has yet been unambiguously identified as a quark star rather than a neutron star. Many observed properties of known compact stars, such as their masses, radii, cooling behavior, and rotational characteristics, can be explained within the framework of neutron-rich nuclear matter. Only in certain extreme cases where inferred properties appear difficult to reconcile with standard neutron star models do some researchers suggest that quark matter might be present. Even then, alternative explanations often remain available, and the observational uncertainties leave room for multiple interpretations. For this reason, discussions of quark stars at the macroscopic level emphasize what is possible under current theory rather than what is established by direct evidence. In the broader landscape of compact object theory, quark stars occupy a conceptual position between neutron stars and black holes. They represent one way in which matter might respond to pressures and densities that push beyond the range where nucleons are effective building blocks, but do not yet reach the conditions for complete gravitational collapse. As such, they provide a framework for exploring how the equation of state of cold dense quark matter could manifest in astrophysical settings, and they guide the search for subtle signatures in mass radius and tidal behavior that might in future observations indicate that at least some compact stars are built from quark matter throughout, rather than from nucleons alone. Strange stars are a particular class of hypothetical quark stars in which the interior is made not just of up and down quarks, but also of strange quarks forming a state known as strange quark matter. In many models, this strange matter is treated as self-bound, meaning that it can be stable at zero external pressure, and could in principle exist as droplets of various sizes from small fragments to whole stellar mass objects. Inside a compact star, strange matter would occupy the bulk of the interior, with pressure support arising from the degeneracy of quarks and from their mutual interactions as described by quantum chromodynamics. In such a configuration, the distinction between core and mantle found in neutron stars becomes less pronounced because the same kind of matter fills most of the volume. Instead, the star can be thought of as a single extended region of strange quark matter, possibly with changes in pairing patterns, or composition with depth, but without the familiar layered structure of nuclei neutron-rich fluid and more exotic components. The degree to which strange quark matter is energetically favoured over ordinary nuclear matter depends sensitively on parameters in the theoretical description, such as the masses of the quarks, the strength of their interactions, and the behaviour of the vacuum energy term that enters approximate treatments of confinement. For some parameter choices, strange matter could be the true ground state of hadronic matter, more stable than iron group nuclei, while for others it is only metastable or not stable at all. Because these parameters are not fixed by direct experiment in the relevant regime, the question of whether strange stars actually exist remains open. In scenarios where strange matter is absolutely stable at high density, a compact star that reaches the conditions for deconfinement in its core might gradually convert to a strange star. The conversion could occur when a small region of strange matter forms and begins to grow by converting surrounding nuclear matter, a process sometimes described as burning, although it is driven by the strong interaction rather than by ordinary combustion. As strange matter spreads outward, it replaces neutron-rich nuclear matter with a quark-dominated phase, changing the equation of state and the star's macroscopic properties. Depending on the rate at which this conversion front moves and the associated release or absorption of energy, the process could be relatively quiet, or accompanied by a burst of neutrinos, gravitational waves, or electromagnetic radiation. However, the details of such conversions are highly model-dependent, and observationally confirmed examples are not yet known. The surface structure of a strange star is one of the most distinctive features in these models. If strange matter is self-bound, it can support itself even without the full weight of an overlying atmosphere, so the density remains high all the way to the star's edge. At the boundary between strange matter and the vacuum, electric charge separation can occur. Quarks in the bulk carry net positive charge, while a thin layer of electrons extends slightly beyond the quark surface, forming an electric field that can be extremely strong over a very short distance. This electric field can influence how particles and radiation interact with the surface. In some treatments, the outermost region is essentially a bare quark surface with radiation emerging from a very thin layer. In others, a crust of ordinary nuclear matter sits above the strange core, suspended by electrostatic forces and limited in thickness by the requirement that nuclei in the crust remain stable against conversion to strange matter. Such a crust, if present, would resemble the outer layers of a neutron star's crust in composition and structure, but would be much thinner, typically extending only a small fraction of the total radius. The presence or absence of this crust affects how the star cools and how it exchanges matter with its surroundings. A strange star with a crust accreting gas from a companion would collect matter on its surface in much the same way as a neutron star, allowing nuclear burning in the accumulated layer, and possibly giving rise to thermonuclear bursts. A bare strange star, on the other hand, would interact with infalling matter differently. Nuclei that strike the surface could be converted directly into strange matter, and the strong electric fields might accelerate charged particles and shape the emergent radiation spectrum. Surface emission from a bare, strange star might differ in detail from that of a neutron star, for example, in the presence or absence of spectral features associated with atomic transitions in a thin atmosphere. At present, however, observational data do not provide a unique signature that clearly demands such an interpretation, so these distinctions remain theoretical possibilities. The outer crust, whether present or not, also plays a role in how the star stores and releases elastic energy. In a neutron star, the solid crust can support shear stresses and can crack or deform under changing magnetic and rotational forces events that are thought to contribute to timing glitches and high-energy bursts. A strange star with only a very thin crust would have less capacity to store elastic energy in this way, which could influence the size and frequency of crust-related events. Some models propose that in strange stars the quark matter itself, if it forms a crystalline or color superconducting phase with spatial structure, might support shear stresses and play a role analogous to that of the crust in neutron stars. The overall mechanical response of the star to spin-down magnetic field evolution and accretion would then depend on both the properties of any crust and the internal quark phases tying macroscopic behavior to microscopic physics. From the standpoint of global structure, strange stars can occupy mass and radius ranges that overlap with those of neutron stars, while also extending into regions that are difficult to reach with purely nuclear equations of state. For example, some strange star models predict very compact configurations with small radii for a given mass, as well as stable configurations at lower masses than typical neutron stars. They can also support sequences in which the radius changes only slowly with mass over a certain range, producing nearly constant radius stars with different masses. These features show up as distinct curves in the mass-radius plane, and provide one way in which observational data on compact objects could in principle differentiate between strange star models and ordinary neutron star models. Gravitational wave observations of merging compact objects add another dimension to this comparison. The tidal deformability of a star, a measure of how much it is stretched by the gravitational field of a companion, depends on how centrally condensed the star is and on the stiffness of its equation of state. Strange stars, especially those with self-bound quark matter, often have lower tidal deformabilities than neutron stars of the same mass, reflecting their higher compactness. When two compact stars spiral together and merge the way they distort, and the phase evolution of the emitted gravitational waves encode information about their tidal properties. Careful analysis of such signals has already begun to rule out some very soft or very stiff equations of state, and future events may further constrain the parameter space in which strange star models remain viable. Until then, strange stars remain a theoretical extension of the quark star idea, representing the case in which strange quark matter forms not just a central core but the bulk of the star and possibly marks a new state of matter that is more stable than ordinary nuclear matter. The possibility of such objects introduces new layers to the structure of compact star theory. In addition to white dwarfs, neutron stars, and black holes, the family of potential remnants now includes stars built from deconfined quarks, with strange stars occupying the subset in which strange quark matter dominates. Whether nature actually realizes this possibility is an open question, but by considering the macro-scale properties of strange stars, especially their surface structure and any outer crust, researchers gain a framework for interpreting unusual compact object observations and for connecting them back to the microphysics of the strong interaction at densities far beyond those accessible in terrestrial laboratories. This layered view from the bulk strange matter of the interior to the possible thin nuclear crust or bare quark surface completes the macro-scale picture of quark-dominated stars and prepares the way for a closer look at the microscopic phases of quark matter itself. At the microscopic level, the matter imagined to fill quark stars and the cores of hybrid stars differs in a fundamental way from the nuclear matter described earlier. In ordinary nuclei and in the outer regions of neutron stars, protons and neutrons act as the basic building blocks. Each of these nucleons is itself a composite object made from quarks bound together by gluons, the carriers of the strong interaction described by quantum chromodynamics. Under everyday conditions, quarks remain confined inside nucleons and other hadrons, and the strong force grows stronger with distance in such a way that isolated quarks are not seen. In ultra-dense environments, however, theory suggests that the balance between confinement and quark motion can change. When the density becomes very high and the average distance between nucleons shrinks to values much smaller than the size of a nucleus, the wave functions of the constituent quarks begin to overlap significantly. In this regime, it may become energetically more favorable for quarks to move in a collective state no longer grouped into individual nucleons, but sharing space in a kind of Fermi sea of quark matter. This deconfined state, if it forms, still obeys the rules of quantum chromodynamics, but the appropriate degrees of freedom are quarks carrying color charge rather than composite nucleons. The quarks in such matter occupy momentum states up to a characteristic Fermi momentum set by the density. Because quarks are fermions, only one quark of a given flavor color and spin can occupy each quantum state. This exclusion principle generates a degeneracy pressure that resists further compression, just as electron degeneracy pressure supports white dwarfs and neutron degeneracy pressure supports neutron stars. But now the relevant particles are quarks with fractional electric charges and color charge. The energy density of the system depends on the quark masses, their interactions mediated by gluons, and any collective effects that arise when quarks pair or condense into correlated states. In practice, theoretical descriptions of cold dense quark matter often use simplified models that capture some features of quantum chromodynamics while remaining tractable. One common approach treats quarks as nearly free particles inside a background that accounts for confinement through an effective vacuum energy term sometimes called a bag constant. In these bag-type models, the pressure inside quark matter results from the motion of quarks minus the inward pull associated with this vacuum energy. If the quark pressure exceeds the confining energy at high density, quark matter becomes stable. The exact value of the bag constant and related parameters is not fixed uniquely by experiment in the relevant regime, so different choices produce different equations of state, some favoring stable, strange matter, others not. More sophisticated treatments include interactions beyond simple confinement, allowing quarks to attract or repel each other depending on color and flavor combinations. These interactions can lead to pairing between quarks in a way loosely analogous to the pairing of electrons in conventional superconductors. In dense quark matter, at low temperature, theory predicts that quarks near the Fermi surface may form Cooper pairs, leading to color superconductivity. In such phases, quarks pair across different colors and flavors in patterns that minimize the free energy. Several pairing patterns have been proposed. In matter containing up-down and strange quarks, a widely discussed possibility is a color-flavor locked phase, in which quarks of all three flavors and all three colors pair in a symmetric pattern. In matter dominated by up and down quarks, other pairing structures involving only two flavors may be favored. Each pattern breaks certain symmetries of the underlying theory and opens energy gaps in the excitation spectrum, meaning that some low-energy quark excitations are suppressed. These gaps in turn influence physical properties such as specific heat transport coefficients and neutrino emission rates. The presence of pairing affects how quark matter responds to changes in temperature and density, and how it exchanges energy with neutrinos and photons. If gaps are large, fewer excitations are available to participate in processes that emit neutrinos, so cooling can be slowed in some regimes. At the same time, the formation and breaking of Cooper pairs can themselves lead to neutrino emission channels. Thus, color superconductivity introduces new possibilities and new uncertainties into the thermal evolution of a compact star containing quark matter. The detailed pattern of pairing, and whether pairing occurs at all for given densities and quark masses, is not yet established, because it depends on the precise form of the quark-quark interaction at high density, which is difficult to calculate from first principles. Strange quark matter adds another layer of complexity. In matter that includes strange quarks alongside up and down quarks, the mass of the strange quark plays a critical role in determining whether strange quarks are abundantly present. If the effective mass of the strange quark in dense matter is not too large, then converting some up and down quarks into strange quarks can lower the overall energy by allowing a more balanced distribution of Fermi momenta among the flavors. In that case, strange quark matter may be energetically favored once the density exceeds a threshold. If the strange quark is effectively too heavy, the energy cost of creating strange quarks outweighs this benefit, and matter remains dominated by up and down quarks. In models where strange quark matter is stable at zero pressure, one imagines that a piece of strange matter could exist in isolation, with its surface bounded by electromagnetic and strong interactions rather than by gravity. In compact stars, this implies that once a region of strange matter forms, it may tend to grow by converting adjacent nuclear or non-strange quark matter into the strange phase driven by the lower energy per baryon. The conversion proceeds through weak interactions that change quark flavors, emitting neutrinos and carrying away energy. The balance between these processes, the surface tension between phases, and the presence of color superconductivity all influence the possible coexistence of nuclear matter, non-strange quark matter, and strange quark matter inside a star. At the microscopic level, the pressure in quark matter comes from several components. There is the kinetic contribution from quarks filling momentum states up to their Fermi momenta, the interaction energy associated with gluon-mediated forces between quarks, and any additional terms arising from the structure of the vacuum in the chosen model. The net result is summarized in an equation of state that relates pressure to energy density or baryon density. This equation of state is the quantity fed into the macroscopic structure equations to determine stellar properties. However, because the microphysics cannot yet be derived reliably for all relevant densities, a variety of parameterized equations of state are used in astrophysical studies, each corresponding to different assumptions about quark masses, interaction strengths, and pairing gaps. One can also consider the possibility that quark matter in compact stars does not form a uniform fluid, but instead arranges itself into phases with spatial modulation. For example, some models predict crystalline color superconducting phases in which the pairing gap varies periodically in space-forming structures that can support shear stresses. Such phases would allow quark matter itself to behave in some ways like a solid, potentially contributing to the star's ability to store elastic energy and to support oscillations. Other models consider mixed phases in which droplets or rods of one phase are embedded in another, forming structures analogous to nuclear pasta, but now at the level of quark matter. These ideas are speculative and rest on delicate balances between surface energies, Coulomb energies and pairing energies, all of which are difficult to compute accurately. The microphysics of quark matter also involves transport properties such as viscosity, thermal conductivity, and diffusion. These quantities determine how quickly heat and momentum are redistributed inside a star and how various modes of oscillation are damped. For example, the damping of certain rotational or pulsational instabilities depends on the bulk and shear viscosities of the fluid. In nuclear matter, these viscosities are set by interactions among nucleons and leptons. In quark matter, They are controlled by quark-quark and quark-lepton interactions and by the presence of pairing gaps. If color superconductivity suppresses low-energy scattering channels, viscosities can change significantly, altering the star's stability against oscillation modes. The microphysics thus feeds into questions about which rotational frequencies are allowed for stable stars, and how quickly certain modes decay. Another aspect of dense quark matter is its role in neutrino processes. Neutrino emission is the main cooling mechanism for young compact stars. In nuclear matter processes such as modified Urca reactions in which nucleons scatter while changing flavor, and emitting neutrinos dominate under many conditions, with more rapid direct Urca processes possible if the composition meets certain thresholds. In quark matter, analogous processes involving quarks, changing flavor can occur. If strange quarks are present, additional channels open. The rates of these reactions are sensitive to pairing gaps and to the phase structure of the quark matter. If gaps are large, direct neutrino emission can be strongly suppressed, leading to slower cooling. If gaps vanish in some regions, or if certain modes remain ungapped, efficient cooling can proceed. Because quark matter is never observed directly, these theoretical rates must be inferred from models and then tested indirectly by comparing predicted cooling curves with observed temperatures of compact stars. Overall, the microphysics of quark and strange matter paints a picture of a rich landscape of possible phases, each with distinct symmetry patterns, excitation spectra, and transport properties. Quantum chromodynamics provides the underlying framework, but the combination of high density and low temperature pushes calculations into a regime where straightforward methods are hard to apply. Approximations, model choices, and numerical techniques fill in the gaps, leading to a range of possible equations of state and internal phase diagrams. At present, this variety cannot be reduced to a single agreed-upon description. Instead, the microphysics supplies families of scenarios, each of which can be used to compute macroscopic predictions for compact stars. In this way, microscopic assumptions about quark masses, pairing patterns, and interaction strengths become encoded in observable quantities such as mass radius, cooling history, and rotational behavior, even though the details of how that encoding works must be explored step by step. The microscopic phases of quark matter do not remain hidden within a compact star. They influence how the star behaves on macroscopic scales across its entire life. Once an inner region makes the transition from nucleonic matter to quark-dominated matter, the way this core stores energy, transports heat, and responds to changes in rotation and magnetic field becomes tied to the properties of the underlying quark phase. In a newly formed compact star, the first important link is cooling. Right after birth in a core collapse supernova, the remnant is extremely hot, and it loses energy mainly by emitting neutrinos from its dense interior. In a purely nucleonic star, neutrino emission proceeds through reactions in which neutrons and protons change identity, while emitting or absorbing leptons with rates controlled by the composition and temperature. If an inner region consists instead of quark matter, neutrino production can occur through analogous processes in which quarks change flavor, for example, converting down quarks into up quarks, or strange quarks through weak interactions. These quark-level reactions can be more or less efficient than their nucleonic counterparts, depending on the density, the relative abundances of quark flavors, and the presence of pairing gaps. If the quark phase allows fast neutrino emission, the core can cool, rapidly carrying heat away from the star's center and lowering its temperature on timescales shorter than expected from nucleonic matter alone. This rapid core cooling then drives heat flow from the warmer outer layers inward, altering the temperature profile, and eventually affecting the surface temperature that an external observer can infer from X-ray emission. If, on the other hand, quark pairing leads to large energy gaps that suppress low-energy excitations, the neutrino emissivity of the quark core may be reduced, slowing the rate at which the star cools. In that case, the core remains relatively warm for longer, and the cooling history resembles that of a stiffer, less emissive nucleonic equation of state. The detailed time evolution of the surface temperature thus becomes a map, although a blurred one, of the interplay between nucleonic and quark cooling channels inside the star. Over decades of observation, measurements of surface temperatures for neutron stars of different ages have been compared with cooling models that include or exclude quark cores and various color superconducting phases. Some combinations of parameters yield cooling curves that drop too fast or too slow relative to representative data and are therefore disfavored, while others remain compatible. This process does not yet single out a unique microphysical description, but it illustrates how quark phases leave an imprint on observable properties through their control of neutrino emission and heat transport. The microphysics of quark matter also feeds directly into rotational evolution. A compact star that rotates rapidly can support certain oscillation modes in which parts of the star move back and forth relative to the rotation axis. Among these so-called R modes involve large-scale fluid motions that are restored by the Coriolis force. If these modes are unstable, they can grow by emitting gravitational waves, draining angular momentum and spinning the star down. Whether an R mode is unstable depends on a competition between gravitational wave driving, which tends to amplify the mode, and viscous damping, which tends to suppress it. The viscosities in question arise from microscopic processes that redistribute momentum and heat, and their magnitudes depend on the equation of state and the phase of the matter. In nuclear matter, shear and bulk viscosities are set by nucleon and lepton scattering. In quark matter, the same roles are played by quark-quark and quark-lepton interactions, modified by any pairing or color superconducting gaps. If a quark phase has low viscosity at a given temperature, R modes may grow more easily, leading to an instability window in which rapidly rotating stars would emit significant gravitational waves until they slow down to a stable region. If viscosity is higher, R modes are more strongly damped, and stars can spin faster without exciting large oscillations. Observed spin periods of young neutron stars and of old millisecond pulsars therefore place indirect constraints on the combination of viscosity, temperature, and composition, and thus on which quark phases can plausibly exist in their interiors. A similar connection appears in the way a star responds to changes in rotation rate on longer timescales. As a compact star spins down through electromagnetic braking or gravitational wave emission, the centrifugal support that helps counter gravity diminishes, and the star's equilibrium structure adjusts. If the core's composition is sensitive to density, these changes in equilibrium can move the inner regions across thresholds between different phases of matter. For instance, a star that initially contains only nuclear matter in its core could, as it spins down and contracts slightly, raise its central density enough to trigger the formation of a quark phase. Conversely, if a region of quark matter exists at birth, but occupies a narrow range in density, evolutionary changes might shrink or expand that region, altering the fraction of the star in the quark phase. Each such change rearranges the internal density profile and moment of inertia. Because total angular momentum is conserved except for what is lost externally, a reduction in the moment of inertia at fixed angular momentum leads to a slight increase in rotation rate. In principle, this can produce small steps or irregularities in the spin evolution superimposed on the longer trend of gradual spin down. Timing glitches observed in pulsars are usually attributed to interactions between the crust and superfluid neutrons in the inner crust, but phase transitions in the core, including the onset or growth of quark phases, have been proposed as additional or alternative contributors in some models. Whether this mechanism is actually realized in nature remains uncertain, yet the possibility shows how microphysical changes can manifest as sudden, macroscopic events. The presence of quark matter may also influence how a star's magnetic field evolves. In nuclear matter, protons can form a superconducting component that affects how magnetic flux is arranged and pinned inside the star. In quark matter, color superconductivity can lead to analogous phenomena for color magnetic fields, and may alter how ordinary electromagnetic fields thread the core. Some color superconducting phases expel certain combinations of gauge fields, while allowing others to penetrate, leading to complex patterns of flux tubes and vortices. As the star spins down and its rotation and magnetic field change, these structures can move or rearrange, transferring angular momentum between different components, and releasing energy in the process. The details are poorly constrained, but in broad terms, the coupling between magnetic flux and superfluid, or superconducting components in the core, determines how rapidly the large-scale magnetic field decays, and how stresses build up in the crust and outer layers. If quark matter adjusts flux differently from nuclear matter, the timescale and pattern of magnetic field evolution can change, with possible consequences for phenomena such as magnetobursts or long-term field decay in old pulsars. Again, alternative explanations exist within purely nucleonic models, and current data do not require quark matter to account for observed behaviors. Nevertheless, any quark phase present in the core would participate in the global magnetic and rotational dynamics. Seismic activity in compact stars provides another channel through which quark microphysics could leave a signature. When a neutron star's crust cracks or yields under stress, it can excite oscillation modes that cause the whole star to ring. In magnetars, the decay or sudden reconfiguration of the magnetic field can trigger intense X-ray or gamma-ray flares, accompanied by quasi-periodic oscillations observed in the tail of the flare. The frequencies and damping times of these oscillations depend on the star's internal structure, including whether the core behaves as a fluid that supports certain wave modes or as a more complex medium with superfluid and superconducting components. If quark matter forms crystalline or spatially modulated phases, it could contribute additional rigidity to the core, or alter the coupling between core and crust, shifting the pattern of oscillation frequencies. Modelling of these events is still developing, and many uncertainties remain, but the basic principle holds. The spectrum of global oscillations reflects the composition and mechanical properties of the interior, so quark phases, if present, would subtly reshape that spectrum. Even in quieter phases of a compact star's life, microphysics influences the approach to equilibrium. Thermal conductivity in quark matter, set by quark scattering pairing, and the presence of leptons determines how quickly temperature gradients smooth out. If conductivity is high heat deposited near the surface, or generated locally by magnetic dissipation, can be transported into the core efficiently, leading to a more uniform temperature. If conductivity is lower, the star can maintain temperature gradients for longer, which in turn modifies the local rate of neutrino emission. The same transport properties affect how quickly the star responds to transient heating events, such as accretion episodes in binaries or sudden magnetic reconnection in magnetars. Observers tracking the rise and decay of X-ray luminosity following such events can in principle infer something about thermal diffusion timescales in the crust and core, and thus about the underlying transport coefficients. Taken together, these links between microphysics and macroscopic behavior show that quark phases, if they exist inside compact stars, would not simply be an abstract detail of the equation of state. They would shape how the star cools, how it spins down, how it emits gravitational waves, how its magnetic field evolves, and how it responds to internal and external disturbances. At the same time, degeneracies in model predictions and uncertainties in the properties of dense nuclear matter mean that many observed behaviors can be reproduced without invoking quark matter. For now, the influence of quark phases on star behavior is best regarded as a set of testable scenarios. Each scenario maps a choice of microscopic state into a predicted pattern of cooling, rotation, magnetic evolution, and oscillation. By comparing these patterns with current and future observations, astrophysicists gradually narrow down which combinations of nuclear and quark phases are consistent with real compact stars and which are not, even if a definitive identification of any single star as hosting a specific quark phase remains beyond reach at present. The search for quark stars and strange stars turns outward from theory to observation into a landscape filled with compact objects that are well measured in some ways and only loosely constrained in others. In this landscape, neutron stars serve as the baseline. Their masses, radii, temperatures, and emission patterns are observed across many systems, and most of those observations are compatible with models in which the interior is made of neutron-rich nuclear matter. To look for hints of quark matter, researchers focus on compact objects whose inferred properties seem difficult to reconcile with standard neutron star equations of state, or on measurements that probe the mass and radius with enough precision to reveal whether some stars are unusually small and dense. One class of systems central to this effort is neutron stars in binary orbits. In binaries where one component is a pulsar and the other is a normal star or a white dwarf, precise timing of pulse arrival times allows astronomers to measure the pulsar's mass through its gravitational influence on the orbit. Over the past decade, such measurements have revealed several neutron stars with masses around or above about 2 times the mass of the Sun. These heavy compact objects are important because they constrain the equation of state any model, whether nucleonic or quark-based, must be able to support at least this much mass without collapsing into a black hole. Equations of state that soften strongly at densities below those reached in these stars are therefore disfavored. At the same time, binary systems in which matter is transferred onto a neutron star provide another type of information. In some low-mass X-ray binaries, the compact star accretes material from a companion through an accretion disk. When sufficient fuel accumulates on the surface, unstable nuclear burning can trigger X-ray bursts. The brightness and time evolution of these bursts, together with the persistent X-ray emission, carry information about the star's radius and surface gravity. By modelling the burst spectra and the effects of general relativistic light bending near the surface, researchers derive constraints on the ratio of mass to radius, and in some cases infer approximate combinations of both. Although systematic uncertainties remain, these measurements suggest that many neutron stars have radii of roughly 10 to 15 kilometers values that are broadly consistent with moderately stiff nucleonic equations of state, but can also be matched by some hybrid and quark matter models. To sharpen these inferences, dedicated X-ray observatories measure pulse profiles from rotating neutron stars with hotspots on their surfaces. As the star spins, the hotspot moves in and out of view, and general relativity alters the apparent path and timing of photons leaving the surface. By fitting the observed pulse shape with detailed models that incorporate light-bending gravitational redshift and Doppler effects, astronomers can infer mass and radius simultaneously for individual stars. The resulting measurements favour compact objects whose radii are neither extremely small nor extremely large for their masses, again leaving room for multiple equations of state, but ruling out some of the softest and stiffest possibilities. If quark stars exist and are markedly smaller for a given mass than typical nucleonic stars, they might show up in this kind of analysis as outliers with unusually small radii. So far, however, measured stars fit within ranges that can be explained by advanced nucleonic or hybrid models, so no single object demands a pure quark star interpretation. Another source of constraints comes from gravitational wave observations of merging compact binaries. When two neutron stars spiral toward one another and merge as seen in gravitational wave events, the tidal forces that each star exerts on the other deform their shapes slightly. These deformations change the phase evolution of the emitted gravitational waves in a way that depends on the star's tidal deformabilities, which in turn depend on the internal equation of state. Softer equations of state, including many with strong quark matter components, often correspond to smaller tidal deformabilities than stiff nucleonic ones. By analyzing the gravitational wave signal, researchers can place bounds on the combined tidal deformability of the two stars and thus on the families of equations of state that remain viable. In the events observed so far, the inferred tidal deformabilities tend to prefer relatively compact stars and to disfavor very stiff large radius models, but they still allow a wide range of hybrid and quark matter scenarios. Future observations with higher signal-to-noise and different mass combinations may tighten these constraints, and could in principle reveal whether some binaries include stars that are significantly more compact than expected for typical neutron stars. Beyond masses, radii and tides, specific compact objects have been proposed as quark star or strange star candidates on the basis of their spectra and cooling behavior. Some isolated neutron stars exhibit thermal X-ray spectra that appear close to featureless blackbody curves with small inferred emission areas, suggesting either small radii or restricted hot regions on otherwise larger stars. In the past, a few such objects were interpreted as possible strange stars with small radii and bare or nearly bare quark surfaces. Later, more refined models incorporating atmospheres, magnetic fields, and non-uniform temperature distributions showed that their properties could also be reproduced by ordinary neutron stars with more complex surface conditions. Similarly, supernova remnants hosting young neutron stars with unusually low, inferred temperatures for their ages have led some researchers to suggest that rapid cooling by exotic processes, including direct neutrino emission from quark matter, might be operating. In other studies, the same data can be explained by nucleonic matter, with enhanced neutrino emission through hadronic processes, or by different assumptions about the star's envelope composition. Thus, while some observations are consistent with the presence of quark matter, they are not uniquely indicative of it. X-ray timing and bursting phenomena provide additional possible hints. For example, in accreting systems, patterns of burst recurrence, burst energy, and persistent emission sometimes suggest surface gravities and compactness parameters on the high side of typical neutron star expectations. There have been proposals that certain high-frequency oscillations seen in X-ray light curves might reflect the presence of very compact stars potentially compatible with quark stars. However, the mapping from observed frequencies to stellar properties is model-dependent, involving assumptions about accretion disk structure, emission geometry, and general relativistic effects. Differences in these assumptions can shift the inferred constraints enough that no single system stands out as a clear quark star candidate. In pulsars, timing irregularities and long-term spin evolution also offer potential clues, but again do not yet provide decisive evidence. Some millisecond pulsars show spin rates that approach theoretical limits set by mass shedding, the point at which centrifugal forces at the equator would overcome gravity. Equations of state that produce smaller, more compact stars can support higher maximum spin frequencies than those with larger radii. The fastest known pulsars therefore constrain the minimum radius possible for a given mass. Very compact quark stars could support even higher spin rates, but the observed maximum periods so far do not require such extreme compactness, and other factors such as formation pathways and accretion histories limit how fast real stars can spin. Attention has also turned to magnetars, whose powerful bursts and giant flares provide a laboratory for high-field, high-stress environments. Some models suggest that if magnetars contain quark matter cores with crystalline or color superconducting phases, the yielding or rearrangement of those cores under magnetic stress could contribute to flare energetics or oscillation frequencies. Others show that purely nucleonic cores with superfluid and superconducting components can reproduce observed behaviors. Without unique spectral signatures or clear evidence of unusually small radii, magnetars remain compatible with both nucleonic and hybrid interior compositions. Across all these examples, a pattern emerges. Observational data on compact stars have become precise enough to rule out some extreme equations of state, and to suggest that many stars are relatively compact and heavy. Yet the data do not differentiate sharply between advanced nucleonic models and models that include quark matter in the core or throughout the star. Proposed quark star and strange star candidates remain candidates rather than confirmed objects because alternative explanations in terms of neutron-rich nuclear matter, sometimes with additional exotic hadronic components, can usually be developed. This does not mean that quark matter is absent. Instead, it reflects the fact that current observations constrain mainly the average stiffness and compactness of the star rather than directly revealing its microscopic composition. As a result, observational hints are best viewed as regions in parameter space, where models with quark matter and models without it both struggle or both succeed, rather than as isolated definitive indicators. The task then is to improve measurements and to combine different observational channels in ways that tighten the allowed ranges. By connecting mass and radius determinations from X-rays, tidal deformability, from gravitational waves, cooling histories from thermal emission, and timing behavior from pulsars and accreting systems, researchers gradually carve out portions of the equation of state space that are compatible with all data at once. Within this shrinking domain, some equations of state incorporate quark phases while others do not. At present, both categories remain viable in various forms, and no single compact object has yet been shown to require a quark star interpretation. Instead, the observational frontier sketches the outlines of where quark stars and strange stars might fit, if they exist, marking a set of possible identities for the most compact and massive members of the neutron star family, while leaving their actual presence an open and carefully framed question. In the broader family of compact stellar remnants, hypothetical quark stars and strange stars sit alongside well-established white dwarfs, neutron stars and black holes occupying a conceptual position between objects supported by known forms of pressure and objects that have undergone complete gravitational collapse. The sequence begins with white dwarfs, which form when low and intermediate mass stars exhaust their nuclear fuel and shed their envelopes. In these remnants, electron degeneracy, pressure balances, gravity and the densities reach values far above those of planets, but far below nuclear density. Their radii extend to a significant fraction of Earth's radius, and their surfaces resemble those of extremely dense compact stars with relatively modest gravitational fields compared with neutron stars. As one moves up in mass and compactness, neutron stars appear as the next step, They result from core collapse in massive stars and are held up by neutron degeneracy pressure and nuclear forces at densities near and above nuclear density. Their radii shrink to only a few tens of kilometers, and their gravitational fields become so strong that general relativity is essential for describing their structure and the behavior of light and matter near their surfaces. Observationally, neutron stars are well supported by multiple lines of evidence: pulsars, X-ray binaries, supernova remnants, and gravitational wave sources all point to compact objects with masses of about 1 to a few times the mass of the Sun and radii of about 10 to 15 kilometers, consistent with nucleonic equations of state. At still higher compactness, black holes appear as solutions of general relativity in which matter collapses inside an event horizon, a boundary from which no light can escape. Stellar mass black holes are inferred in X-ray binaries and in gravitational wave mergers of compact objects, whose masses and lack of tidal signatures are consistent with horizons rather than surfaces. Between the densest confirmed neutron stars and the lightest stellar mass black holes lies an interval where theory allows, but does not demand, the presence of quark-dominated stars. In many models, the maximum mass that a neutron star made purely of nucleonic matter can support is close to the highest masses observed so far. If the true maximum mass for nucleonic stars is only slightly above about 2 solar masses, compact remnants heavier than that value must continue collapsing into black holes. In mixed or quark-dominated equations of state, the situation can be more nuanced. A softening of the equation of state at intermediate densities when quark matter first appears can reduce the maximum mass for stars without quark cores, but a subsequent stiffening at higher densities in the fully developed quark phase can create a second branch of stable configurations. On this branch, stars with quark cores or stars composed mostly of quark matter can support masses comparable to or larger than those of the heaviest observed neutron stars, while remaining smaller in radius and more centrally condensed. In such pictures, the landscape of compact remnants includes neutron stars on one branch, hybrid stars and quark stars on another, and black holes beyond the point where no pressure can balance gravity. The mass-radius diagram provides a useful way to visualize this structure. Each equation of state traces out a curve of possible configurations starting from low central density, where stars are less massive and larger, and moving toward higher density, where they become more massive and smaller. White dwarfs occupy one region of this diagram with low mass and large radius. Neutron stars populate a more compact region, with higher mass and much smaller radius. Black holes, if represented in terms of an effective radius such as the event horizon radius, occupy an even more compact domain. Quark stars and strange stars, if they exist, would inhabit the band between neutron stars and black holes, either overlapping with the most compact neutron star configurations or extending into regions of even smaller radius for a given mass. In some equations of state, the transition from neutron stars to quark stars appears as a continuous sequence, while in others it is marked by a distinct gap or kink where a new stable branch begins. Observationally measured masses and radii of compact stars populate part of this diagram, but leave the region of most extreme compactness sparsely sampled. The heaviest confirmed neutron stars define the lower boundary for viable equations of state, and the absence so far of stars with very small inferred radii suggests that many stars have interiors compatible with nucleonic or modestly softened hybrid matter. Yet the possibility remains that some compact objects, especially those with properties at the edge of current measurements, lie on a quark-dominated branch. In this view, The phrase "the densest object before a black hole" does not specify a single unique class of star, but instead refers to the most compact stable configuration that nature actually realizes. That configuration might be an extreme neutron star with nuclear matter compressed to its limits, a hybrid star with a quark core and a nuclear mantle, or a quark star composed largely of deconfined quark matter and perhaps strange quark matter throughout. Which of these options is realized depends on the true equation of state of dense matter, which remains uncertain. The conceptual role of quark stars in this hierarchy is to provide one possible answer for what happens when neutron-rich nuclear matter is pushed beyond densities at which nucleons remain effective degrees of freedom but before full collapse into a black hole. They embody the idea that the strong interaction may allow new states of matter that are stable enough to support a whole star against gravity. In doing so, they connect microphysical descriptions in quantum chromodynamics to macroscopic astrophysical objects extending the sequence of remnants beyond white dwarfs and neutron stars into a regime where matter is built from quarks rather than nucleons. From the standpoint of stellar evolution, quark stars, if they form, would share many features with neutron stars. They would arise from core collapse in massive stars, or possibly from the merger of neutron stars in binary systems. The difference would lie in the internal pathway taken during and after collapse. In one scenario, the core collapses to nuclear densities and stabilizes as a neutron star, which later evolves until its core density crosses the threshold for quark matter, gradually or abruptly converting into a quark star. In another, the core may overshoot the nucleonic regime and enter the quark phase directly during the collapse, forming a quark star soon after birth. In both cases, the observable signatures during the supernova and the early stages may differ only subtly from those of neutron star formation, because much of the energy release is carried by neutrinos and occurs deep in the interior. In later evolutionary stages, accretion, spin-down, and magnetic field evolution would proceed in ways similar to those of neutron stars, with differences governed by the altered internal structure and equation of state. These differences, as discussed previously, could influence cooling rates, maximum spin frequencies, tidal deformabilities, and the response to stress, but they would not necessarily produce new categories of observational phenomena that stand apart from neutron stars and black holes. Instead, they would shift the detailed properties of some members of the compact object population. In this context, quark stars become part of a continuum of possibilities rather than a sharply separate class. The densest confirmed objects are still neutron stars. The least massive confirmed black holes occupy a higher mass and compactness regime. Between them lies an interval where the nature of matter is uncertain and where several theoretical descriptions can be constructed. Some of these descriptions involve only nucleons and leptons, possibly with additional hadronic species. Others include quark matter in the core or throughout the star. All can be tuned to satisfy current observational constraints on mass and radius, at least within uncertainties. The role of quark stars in this continuum is to represent those models in which quark matter does take over in the densest stable configurations. They provide a template against which observations can be compared as measurements improve and as new data from gravitational waves and X-rays add more points to the mass radius and tidal deformability diagrams. For now, the hierarchy of compact remnants remains anchored by white dwarfs, neutron stars and black holes, with quark stars and strange stars as carefully framed possibilities that may populate the densest stable region if the equation of state of cold dense matter allows it. In that region, the idea of the densest object before a black hole reflects the limit of supportable compactness under the true microphysics of the strong interaction. Whether that limit is set by nucleonic matter alone or by a quark-dominated phase remains one of the central open questions at the junction of nuclear physics, particle physics, and astrophysics. And it is this junction that defines the place of quark stars among compact remnants. Constraints on the behavior of dense matter do not come only from distant stars. They also arise from experiments and theory on Earth, where nuclear physics and particle physics set boundary conditions on any equation of state that is meant to describe the interiors of compact stars and the possible existence of quark stars. In laboratories, nuclei are created scattered and broken apart under controlled conditions, and their properties reveal how protons and neutrons interact at distances comparable to their own size. These interactions determine the binding energy of nuclear matter at densities near that found in the centers of ordinary nuclei, the compressibility of that matter, and the way its energy changes when protons and neutrons are present in unequal numbers. Together, these quantities fix the saturation point of nuclear matter, the point at which it prefers to sit at a particular density and binding energy per nucleon. Any equation of state that aims to describe the outer core of a neutron star or the nuclear layers above a quark core must reproduce this behavior at densities around saturation. If it does not, it would contradict well-established nuclear data. Modern descriptions of nuclear matter at these densities often start from forces between nucleons, derived from underlying symmetries of quantum chromodynamics, and formulated in frameworks such as chiral effective field theory. In these approaches, the interaction between two nucleons includes not only pairwise forces, but also contributions from three nucleon forces, in which the presence of a third particle changes the interaction between the other two. Calculations of neutron-rich matter using these methods produce bands of allowed pressure and energy density, at densities up to about twice the saturation density. These bands, though not infinitely precise, set limits on how stiff or soft nuclear matter can be in this regime. Equations of state that deviate strongly from these bands are disfavored because they would require nuclear forces different from those inferred from scattering experiments and nuclear structure data. Above about twice the saturation density, direct experimental guidance becomes weaker, but other probes still provide information. Heavy ion collisions in which large nuclei are accelerated to high energies and smashed together briefly create compressed and heated nuclear matter. The matter in these collisions expands and cools rapidly, and detectors record the pattern of emitted particles. By comparing these patterns with simulations that include different assumptions about the nuclear equation of state physicists, infer how compressible nuclear matter is and how its pressure rises with density in the regime reached during the collisions. Although the conditions in these experiments differ from those in the cold, dense interiors of neutron stars, they still help to constrain the stiffness of the equation of state over a range of densities that overlap with the lower part of the neutron star core. Too soft an equation of state would lead to stronger compression and different flow patterns than those observed. Too stiff an equation of state would produce weaker compression. The allowed window from heavy ion data combined with nuclear structure and chiral, effective field theory calculations narrows the range of acceptable pressure versus density curves at moderate densities. Particle physics provides additional constraints through studies of individual hadrons and their interactions. Measurements of hypernuclei, which are nuclei containing hyperons with strange quarks, indicate how such particles behave in dense environments. These data inform models that include strange baryons in neutron star cores and limit how strongly such additions can soften the equation of state without conflicting with observed heavy neutron star masses. Similarly, measurements of meson properties in Nuclear matter, such as shifts in energy levels, constrain how mesons might condense in dense environments. All of these pieces feed into the hadronic side of the equation of state, shaping the part of the curve that must be matched smoothly if a transition to quark matter occurs at higher densities. Quantum chromodynamics itself is probed directly in experiments and in numerical simulations, but each method has limits. High-energy colliders create a quark gluon plasma at very high temperature and relatively low net baryon density, a regime relevant for the early universe, but different from the cold dense matter in compact stars. Lattice simulations of quantum chromodynamics, which discretize space and time on a grid and compute thermodynamic properties numerically, work reliably at high temperature and low net density. At high density and low temperature, technical difficulties impede straightforward calculations, so direct first principles results are scarce. Nevertheless, lattice studies provide important benchmarks, showing, for example, how the pressure of hot quark matter approaches that of a weakly interacting gas at very high temperature. These results guide the construction of effective models for dense quark matter, even though the regime of interest for quark stars lies beyond the region where lattice calculations are currently most precise. On the theoretical side, models of quark matter used in compact star studies must be tuned so that when extrapolated down to lower densities, they do not contradict known properties of hadrons and nuclear matter. A model that predicts deconfinement at densities only slightly above saturation density, for example, would imply that nuclei themselves are unstable, or that ordinary nuclear matter in laboratories should already show signs of deconfined quarks, which is not observed. To avoid this conflict, parameters are chosen so that quark matter becomes energetically favorable only at densities several times higher than saturation, well beyond those present in finite nuclei. This tuning ensures consistency with terrestrial data, while allowing for the possibility that quark matter emerges in the deep cores of the most massive compact stars. Earth-based measurements also constrain the symmetry energy of nuclear matter, which describes how the energy changes as the proportion of neutrons to protons varies. The density dependence of the symmetry energy affects the pressure in neutron-rich matter, such as that found in neutron star crusts and outer cores, and thus influences the star's radius for a given mass. Laboratory observables such as neutron skin thicknesses in heavy nuclei, where the distribution of neutrons extends slightly beyond that of protons, are sensitive to the symmetry energy. By measuring these skins and combining the results with theory, physicists derive preferred ranges for the symmetry energy and its slope with density. These ranges then propagate into constraints on neutron star radii. Since quark star and hybrid star models must agree with, or at least not blatantly violate these constraints at densities where nuclear degrees of freedom still dominate the allowed forms of the equation of state, at higher densities become more tightly bounded. In this way, terrestrial experiments shape the low-density end of any viable equation of state and restrict how rapidly it can change as density increases. Additional information comes from precision studies of weak interactions in nuclei and from measurements of beta decay lifetimes, which fix aspects of how matter achieves beta equilibrium, the balance between different particle species under weak interactions. In neutron stars and potential quark stars, beta equilibrium determines the composition of matter at a given density. For nuclear matter, the relative fractions of neutrons, protons, electrons, and muons are set by conditions similar to those probed in nuclear beta decay. For quark matter, the fractions of up, down, and strange quarks together with electrons or other leptons must satisfy similar constraints. Equations of state that assume compositions far from what beta equilibrium would produce are inconsistent with the basic principles already confirmed in the laboratory. Thus, even though the density regime in stars is extreme, the underlying reaction channels and equilibrium conditions rely on weak interactions measured under more familiar conditions. The net effect of these Earth-based constraints is to carve out a region in the space of possible equations of state that any astrophysical model must inhabit. Within this region, there is still room for significant variation, especially at densities a few times higher than nuclear saturation, where direct experimental guidance is weakest. Some equations of state in this allowed region are purely nucleonic. Others include hyperons, meson condensates, or other exotic hadronic components. Still others introduce a transition to quark matter at some threshold density. All must, however, reproduce nuclear properties at lower densities, honor bounds from heavy ion collisions, respect symmetry, energy constraints, and remain compatible with weak interaction physics. Models that fail on these counts are set aside regardless of whether they produce interesting quark star sequences. In this way, laboratory physics does not directly reveal quark stars, but it limits which quark star scenarios can be considered realistic. Any hypothetical quark star or strange star must be built from a quark matter equation of state that is consistent with these terrestrial constraints when extrapolated appropriately. Conversely, if future measurements on Earth significantly tighten the allowed bands for nuclear pressure symmetry energy and hyperon interactions, they will further narrow the window in which quark matter can appear in stars without contradicting known nuclear physics. The interplay between Earth-based experiments and astrophysical modeling thus functions as a two-way bridge. Experimental results inform which dense matter models are plausible, and astrophysical observations highlight which aspects of nuclear and quark matter physics need more precise constraints. In the context of quark stars, this bridge ensures that even the most speculative models remain anchored to the behavior of matter as it is actually measured in the laboratory, providing a necessary grounding before any claims about the densest objects before black holes can be made. The question of whether quark stars and strange stars exist in nature moves gradually from theoretical speculation toward testable science as observational capabilities improve. Each new instrument and each new kind of measurement adds another way to probe the interiors of compact stars' tightening constraints on the dense matter equation of state, and reducing the range of models that remain compatible with data. In the coming years and decades, several observational approaches converge on the same goal to measure the masses, radii tidal properties, cooling histories, and emission patterns of compact objects with enough precision and diversity that different internal compositions, including those with quark cores or quark-dominated interiors, can be distinguished from one another. One key avenue lies in more precise mass and radius measurements from X-ray observations. Instruments that time X-ray pulses from rotating neutron stars with hotspots map how light curves vary as the star spins. General relativity bends light near the compact object, and the amount of bending depends on the ratio of mass to radius. As data accumulate for more stars and as models of surface emission, atmosphere composition, and magnetic geometry improve, the uncertainties on mass and radius shrink. If future measurements reveal compact stars with masses and radii that lie well outside the region allowed by any purely nucleonic equation of state, consistent with laboratory, nuclear physics attention will turn naturally to equations of state that include softer inner cores and stiff high-density phases, many of which involve quark matter. Conversely, if all measured stars continue to fall within the region explainable by advanced nuclear models, the parameter space available for quark stars will narrow, confining them, if they exist, to a subset of the most extreme objects. In parallel, gravitational wave astronomy continues to develop as a tool for probing dense matter. Each merging binary containing compact stars, whether two neutron stars or a neutron star and a black hole, carries information about the tidal deformability of the neutron-rich object. As detectors gain sensitivity and new events are recorded with higher signal quality, the range of masses and mass ratios sampled by observations expands. By combining many events, astronomers can build up a statistical picture of how tidal deformability varies with mass. If some events involve stars that are markedly more compact than typical neutron stars, their waveforms would show smaller tidal effect pointing to stiffer cores and higher central densities. Detailed comparisons between these observations and families of equations of state would then reveal whether models with quark matter are preferred or whether nucleonic models suffice. Future generations of detectors with improved low-frequency sensitivity will follow in spirals for longer and resolve tidal signatures more clearly, giving tighter bounds on the internal structure of compact stars and on the possible presence of quark-dominated interiors. Another promising direction comes from continuous gravitational waves emitted by rotating compact stars with slight asymmetries. If a star contains a non-axis symmetric deformation in its crust or core, it can radiate gravitational waves at twice its rotation frequency. The amplitude of these waves depends on how rigid the star is and how much strain it can support. In stars where quark matter forms crystalline or spatially modulated phases, the core might contribute to the overall rigidity in a different way from a purely nucleonic core. Detecting continuous gravitational waves and measuring their amplitudes would therefore provide information about the star's internal ability to support deformations. Even upper limits in the absence of detections already constrain the maximum ellipticity for certain nearby pulsars. As search methods improve and detectors become more sensitive, these constraints will either reveal small but finite deformations or push the allowed ellipticity lower, narrowing the range of possible internal structures and phases. Thermal evolution remains a third observational pillar. Long-term monitoring of surface temperatures for isolated neutron stars and for compact objects emerging from transient accretion episodes builds up a sample of cooling curves. More precise distance measurements, improved models of neutron star atmospheres, and better estimates of ages from surrounding supernova remnants all refine these curves. Theoretical models that include different combinations of nucleonic and quark phases, each with specific neutrino emission and heat transport properties, can be confronted with this ensemble of observations. If a subset of stars shows cooling behavior that consistently favors rapid core neutrino emission, beyond what hadronic processes can provide models with quark matter, especially those without strong pairing gaps, would gain support. If instead, all observed cooling tracks lie comfortably within the range produced by nucleonic equations of state, with modest enhancements from additional hadronic components, tighter bounds on quark phases would follow. Either outcome would represent progress because the observational data and theoretical models would be linked more tightly. At the same time, detailed timing of pulsars continues to offer a window into internal dynamics. Arrays of millisecond pulsars used as timing networks for gravitational wave detection. Record pulse arrival times with high precision over many years. Any systematic departures from simple spin-down laws such as those associated with glitches timing noise or long-term changes in spin-down rate can be analyzed for patterns. If statistical studies show features that match predictions from models in which core phase transitions occur as stars spin down and their central densities rise, those phase transitions, possibly including the onset of quark matter, could become more plausible. if no such patterns appear, or if alternative explanations based on crust superfluidity and magnetic field evolution fit the data more naturally. The role of quark phases in timing irregularities would be correspondingly limited. Future radio facilities with larger collecting areas and wider bandwidths will provide more pulsars and more precise timing, strengthening this line of inquiry. Magnetars, with their intense magnetic fields and episodic high-energy flares, serve as laboratories for studying the interplay between magnetic stress and the mechanical properties of compact star interiors. Observations of quasi-periodic oscillations in the tails of giant flares already give some information about global oscillation modes. As X-ray and gamma-ray observatories gain sensitivity and energy resolution, and as more flares are detected, the mode spectrum can be mapped more completely. The frequencies and damping times of these modes depend on the star's mass radius, crust thickness, magnetic field configuration, and core composition. Comparisons between observed mode patterns and models that include nuclear matter alone or nuclear matter, plus various quark phases, will allow researchers to assess whether cores with exotic phases including crystalline or superconducting quark matter give a better match to the data. This assessment will unfold gradually as observations and modelling of magnetoseismology improve. In addition to astrophysical observations, advances in laboratory physics and theory will continue to refine the boundaries that any viable dense matter model must respect. New measurements of neutron-rich nuclei improve determinations of symmetry energy parameters, and more detailed studies of hyperon interactions will sharpen the hadronic side of the equation of state. Progress in heavy ion collision experiments at facilities designed to probe higher net baryon densities will extend constraints on the pressure of dense nuclear matter. On the theoretical side, developments in methods for dealing with quantum chromodynamics at finite density, even if indirect, will help guide the construction of more realistic quark matter models. As these terrestrial constraints tighten some dense matter equations of state that currently allow quark stars will become inconsistent with laboratory data and will be set aside while others will survive with narrower parameter ranges. The interplay between Earth-based experiments and astrophysical observations thus grows stronger, with each side informing the other. Multi-messenger observations combining electromagnetic radiation, gravitational waves and neutrinos from single events offer another way forward. A core collapse supernova that is detected in all three channels would provide a rich data set spanning the birth of a compact remnant, its early cooling, and any associated gravitational wave emission from instabilities. If the remnant undergoes a phase transition in its core during or shortly after formation, perhaps involving the onset of quark matter, the change in internal structure could leave signatures in the neutrino light curve, in the gravitational wave signal, or in the timing and spectrum of electromagnetic emission. Modelling such events requires careful treatment of both hadronic and quark phases and their couplings, but the potential diagnostic power is considerable. As neutrino detectors grow more sensitive and gravitational wave observatories expand their reach, the likelihood of catching such informative events increases. Across all of these efforts, the goal is not to force a particular outcome, but to let data rule out broad classes of models and to identify those equations of state that remain viable. Among the surviving models, some will involve only nucleonic and hadronic matter, and others will include quark matter in inner cores or throughout entire stars. The distinction between a neutron star pushed to its densest possible state and a quark star built from deconfined quarks will then rest on whether any combination of observations consistently points to internal conditions that cannot be reproduced by nucleonic models alone. The path to that distinction is incremental. Each new measurement of mass radius tidal deformability cooling behavior or timing adds a small piece of information about how matter behaves at densities far beyond those of normal nuclear matter. As these pieces accumulate and as models become more tightly constrained by both astrophysical and laboratory data, the allowed description of the densest stable compact objects narrows. In this gradual way, future tests may show that the densest objects before black holes remain neutron stars with extremely compressed nuclear interiors, or they may indicate that at least some of those objects contain cores or hole interiors in which quarks rather than nucleons provide the pressure that holds gravity at bay. In either case, the observational programs and theoretical advances designed to answer this question converge on the same frontier in physics, where the structure of compact stars and the properties of dense matter meet.